Good afternoon, everyone. Thank you for coming to another Ezra Roundtable seminar series. My name is Andreas Malikopoulos. I'm a faculty with the Civil Environmental Engineering Department, also associated with the Systems Engineering. Today is my distinct pleasure to welcome today's Ezra speaker, Professor Alex Bayen, who is not only a prominent, globally recognized leader in optimization and control and transportation systems, but also a very valued friend and colleague. So Professor Bayen is Liao Chao Professor in the Department of Electrical and Computer Science at Berkeley, UC Berkeley. He is also the Associate Provost at Berkeley Space Center and the Director of CITRIS and Banatao Institute. He received his master's and PhD degrees from Stanford University, and then he joined the faculty at UC Berkeley and has been doing groundbreaking research in the millennium sensing and traffic modeling since then. One of his early on accomplishments was the Mobile Millennium Project, where he essentially, with his students, he demonstrated in 2008 that we can replicate traffic flow by using the Nokia cell phones. You might be too young, you might have not met with these Nokia cell phones in 2008, and nowadays we have cell phones and smartphones that we can estimate the traffic, but recall 17 years ago, there was no way that you can have an estimation of the traffic if you go from point A to point B. So Professor Bayen and his students showed that they can replicate the traffic flow and have estimation of traffic flow by using the Nokia cell phones. And then since then he has done a lot of other nice accomplishments in this area of mobile sensing and traffic modeling. He has received numerous awards, including the Picasso Award from the White House, the Ruperti Prize, the NSF Career Award, just to name a few, the IPS Outstanding Research Award, this is just to name a few, from a very long list. So I would encourage you to go online and check out his bio. And he's also an IEEE fellow. He has published, he has authored and edited 5 books and more than 250 publications in this area of optimization, control, and transportation. He's also the PI for the cycles and flow projects. These projects, essentially, he uses the reinforcement learning to help us understand the implications of the phantom traffic jams and also the mixed traffic environment when you have connected automated vehicles and human-driven vehicles. And I believe that today he's going to talk about this. So with this, I would like to welcome you, to join me in welcoming Professor Alex Bayen.
Thank you for the warm introduction, and thank you for your hospitality. It's always a pleasure to visit Cornell and have a lot of old friends, new friends, very familiar faces in the audience. Okay, today I'm going to talk about the Mega-Vendor test, but mostly I'm going to talk about mixed autonomy and show trends that we observed in the industry and that we try to accelerate. So if you think about the history of self-driving vehicles in one slide, the very first self-driving vehicles in California was deployed by UC Berkeley in 1997, Steve Schladover. These vehicles are all automated, platooning, going really fast. Lots of instrumentation, that's Gen 1, you have to instrument the vehicles and the pavement. Then the DARPA Grand Challenge came, and then the idea was we put like $3 million of equipment in a vehicle and try to get them from LA to Los Angeles autonomously, and that completely revolutionized an industry, because when DARPA did that, essentially, the results were not as far as they were expecting. They didn't succeed in entirety, but suddenly people realized that it's only a matter of time before instrumentation gets small enough and cheap enough that it can scale. So later, Google did their Gen 1 automated cars that we used to see around 2013-ish in Mountain View that had a lot of challenges, and then things forked. Essentially, Tesla started to gradually grow from level 1 to level 5. 1 is, or 0 is your pop and mom's car, 0 automation. 5 is there's no steering wheel, no supervision. It's a fully self-driving. Tesla essentially started to push things along the scale, 1.1, 1.2, 1.3, and certainly getting into 2, and hoping over a decade to go to 5. Waymo did the complete opposite. Waymo went straight to level 5, very geofenced, very specific routes, very specific things at specific times of the day, progressively expanding. And essentially, the industry has branched. They will reconnect again, ultimately, because it'll all become the same. But that became two very, very different threads in the self-driving vehicle industry. And so it brings me to the concept that we all have to live with for the next probably 10 or 15 or 20 years, which is essentially the coexistence of vehicles with a certain degree of automation, so in red here, and vehicles that are driven by humans and have no automation, or at least are driving without any automation on, just humans driving. That's the reality of traffic probably for the next couple of decades to come, and that's where our work fits. Essentially trying to understand what can you do when you have systems where humans coexist with machines. Kathy, who is now a professor at MIT, was a former student. She's one of the few people who really cornered that term mixed autonomy, which has become a standard in the industry since. Now, when we started that work, the motivation really came from the US Department of Energy, Ruben Sarkar. In fact, that's when I met Andreas at Oak Ridge in my very, very early days. And Ruben Sarkar, who was the Deputy Assistant Secretary under Barack Obama, was showing this graph that was from work of McKinsey, showing that in the world of mixed autonomy or full autonomy, if things were done wrongly, you would screw us up by essentially making the energy footprint of traffic explode, like sending your empty self-driving vehicles, pick up your kids, they get stuck on the freeway, they turn around the block and never park because there's no spot, and essentially burn infinite energy. Or if you do it well, maybe you could reduce the footprint of energy by up to 60%. And that's the reason in some ways that if you do different things, maybe you can go faster, you burn more energy, not good, but on the other hand, if you do it platoon, then you can recover the energy lost otherwise. And so that's the motivation of what we did. We figured we're not going to change traffic congestion. That's a very hard problem, but maybe with given demand, given supply, we can make things more efficient. So when we embarked on that project, the idea was that some level of automation is available. If you buy the latest car, even if it's not a Tesla, there is some level of automation, some automated cruise control or something like that. But mostly wherever you drive, you can be assured that communication will be very crappy. You're going to lose cell phone reception. And so vehicles are not connected with each other, except in very specific cases. And then if you're connected to some cloud, it's going to be very crappy. Low bandwidth, high latency. And so the reality was like, can we build some algorithms that work with this? So very hard, very strong capability in the background. You can run infinite power stuff on the cloud, sure. Very crappy communication to some vehicles. And then most of the other vehicles driven by humans. That's the context. So in my entire talk, the color code is every time you see a red vehicle, it's some level of automation. The blue vehicles are vehicles that the local vehicle can sense. Usually you can sense forward, backwards, or you have some information somehow. So you can see some partial state of the blue vehicles. And then there's a bunch of white vehicles and you have no idea what they're doing because they're driven by humans and you cannot see them. And so the idea is that what we try to do is something that conceptually looks like this, where some small, very small proportion of vehicles you can control through our algorithm, so the red vehicles. They can see some blue vehicles for in some ways, and then there's a bunch of white vehicles in the middle that they cannot see. And all the algorithms I'm presenting today essentially work in that context, and the idea is like, how far can you push that context? And so this is not a theoretical talk today. I'll be back hopefully in April with more theory, but this is really more of an engineering talk, explaining what architecture we built, how does it work, and give you a sense of some algorithms inside some of these boxes. So this is my frame for today. What we built over the years, we built 3 versions of this, and we run one at scale with 100 vehicles, is a server-side system that does planning across all the vehicles, that uses very crappy networks, the cell phone network, to send some very high-level commands to local vehicles that run local controllers. And because we're running with different cars, Nissan, Toyota, and GM, we have different boxes, and the boxes have different algorithms and different architectures. So today, I'm going to walk you through this. I'm going to go inside some of the boxes, and I'm going to show you some of the algorithms inside of the boxes, and show you how we implemented it in real life. So maybe we can start with what happens in a vehicle first, and then we'll step back and look at a much higher level. So this project started in 2016, before the hype of deep reinforcement learning, or right when deep reinforcement learning was undergoing its first recent revolution. Deep reinforcement learning operates along a framework that probably you've studied in class. So you have agents that provide some form of action, and then you have some form of environment, could be black box or not, that provides the state of the system at a given time later, and some reward, and based on the reward, you know what to do next. So this is a very general framework for deep reinforcement learning, where you try to maximize some form of expected cost of cumulative reward over time based on the policy that you develop. So this is your controller. So our job, when we started this, we were not even considering communication between the vehicles. We were just considering what can we use in deep reinforcement learning, and why would we do that, to maximize the total efficiency of the system based on vehicles not even talking with each other, but just doing a local optimization. And Kathy Wu, who is now a faculty at MIT, Eugene Veditsky, thank you, who is sitting in the back, and Woody Craigie, who is now at Google, together with a team came up with this framework, which was the first historical integration of deep reinforcement learning libraries, at the time RLib and RLab, with micro simulation tools, Sumo open source and IMSON closed, on the cloud. And the cloud at the time was AWS, because that was the cloud. And in fact, the first historical version of IMSON, which is a commercial product of Siemens, for the cloud was built for us for this project. And of course, now it's available on the cloud for everybody, but we're the first one to use it. So I think the vision at the time, and it's really to Kathy's credit, who was the student who had that vision, is really that it became actually computationally feasible around 2017 to run microsimulations, which were previously extremely hard to run. And it became also feasible to do reinforcement learning on these models, which are very expensive, which again, 5 or 10 years earlier would not have been possible. So then came this interesting experiment that was created by another student of mine, Dan worked with Benedetto Piccoli, Benny Siebold, and John Sprinkle, where they demonstrated in 2017, I think, that if you insert one self-driving vehicle inside a ring, you can stop the stop-and-go oscillations that are happening. So here the idea, the idea was, you've probably seen this video many times, or similar videos many times. If you just ask humans to drive in a circle and follow the person in the front, what happens after a while is this. Essentially, there's oscillations, and cars stop and go, and stop and go. And that's because humans are very bad at regulating. So here, the vehicle is not even self-driving right now, or just until it turned red. The vehicle essentially was just driven by a human. And then you can see these oscillations happening back and forth and back and forth. That's because humans are very bad at regulation. Now here, the arrow just turned red. So the vehicle is now turning on some simple controller that they built. And you can see that very quickly, a single self-driving vehicle is able to stabilize the oscillation. So oscillations are known in control theory as string instability. There's a whole fantastic paper by Swarup and Hedrick of 1996 that studied this, and many papers since. And essentially, this was the first time in history that a group managed to stop string stability with a single drive vehicle at different speeds. And what they demonstrated at the time is that they could improve the energy efficiency of all the vehicles, not just the self-driving vehicle, by 42%. So it's crazy, right? If 22 humans drive, they burn a lot of gas because they are unable to regulate the circle. And then you put one self-driving vehicle with a simple controller, it smooths it out, and it saves 42% of energy. So for us, this was fabulous because that gave us a sense that maybe what they did on the ring, we could do on a freeway. So the next year, Kathy Wu came up with this model in Sumo. So self-driving vehicle can only see the vehicle in the front. And as you can see, a good traffic model will be able to replicate what human does. So because of the inability of human-driven vehicles, which have a different model, modeling the humans, essentially the system is equally unable to control itself. And then when the autopilot is turned on now, it's able to regulate. That was done in 2018. So now you're probably wondering, well, why am I showing you a simulation of 2018 of something that was done in the field in 2017, the year before? If they did it in the field, what's the point of simulation? The point is that the previous algorithm is an expert algorithm. It's a control theoretic algorithm explicitly written for which you can prove stability. This is a policy developed by deep reinforcement learning without any knowledge of the dynamics of the white vehicles, which are treated as black box. In other words, you take a deep reinforcement learning library, you train it on a black box simulator, and it comes up with the same policy, except he has no idea how many cars are there. It's just seeing a reward on the basis of the state of the system. So for us, it was a leap forward because we realized that if we can do this now without explicit models of the system, maybe there's a chance we can do it on a freeway. It's very impossible to model a freeway. There's too many vehicles, it's too complex. But maybe there's a chance deep reinforcement learning can figure out a policy, and that's what we're going to pursue. So that for us was a branch from essentially classical methods. And so what we try to do then,
Just a quick question about the learn policy. Then you actually, because these are deep neural networks,
Yeah.
challenging to actually verify
Yeah.
that they do result in a stable system. So did you prove that in fact this policy stabilizes the system, or it's empirically appears to stabilize?
Yeah, we can't prove it. We have no idea. We tried it on a variety of distributions of possible initial conditions, models, perturbations. Most of the time it works on the distributions we have, but we cannot prove anything. And I mean, even years later, we still have no way to provide a formal method that gives us guarantees. There's a lot of interesting work by George Papas that is essentially done forward reachability on neural nets, where I think maybe that can be applied, but somehow we've not managed to scale it there. So in some ways, we're putting a lot of faith in these algorithms. And the closest we've gotten to a proof is you take the neural net, you take a polynomial fit of the mapping, if it's tractable enough, and then you prove something on the polynomial. So then the neural net just is used as an inspiration for your explicit controller, but then you dump it because you don't want to take multiple derivatives. And this is super black box, and this is super applied, and that's a road we chose. It's a bit of a scary road, but that worked for now. So then we figured, okay, can we try to see if we could generalize this? So for example, we tried an interesting problem of transfer learning where you train the vehicles on a ring and then you put them in a situation they've not seen before, like a merge. So for example, the merge here is, it essentially injects vehicles, and you see as it injects vehicles, it creates these back propagating waves, so you'll see them happen more and more. And the back propagating waves essentially are where the energy inefficiency happens. And what's interesting is that now, notice, it actually learned to stop. So you have essentially transformed a self-driving vehicle into a traffic light. And that's a policy it actually learned on the ring. And so if you look at the explanation of why, it's actually fully intuitive. That's the work of, again, Abudi and Eugene. So you have the merge here, and every time you inject a vehicle, this is time and space, every time you inject a vehicle, you take some space, so it creates this back propagating wave, and you can't control that. But if you have learned a policy that if you can see ahead of you that there is a slowdown, then the algorithm somewhere has learned that it should wait. And what it does is now that you have injected the car, so the car creates essentially the wave. The vehicle knows this because it has access to the blue vehicles ahead, and it learns to stop at the traffic light and reconnect exactly where the two merge. So that's interesting because that's way more efficient from an energy standpoint, but that's also a transferred policy that it learned in a completely different setting. So they try to do some penetration work to figure out, okay, so how many vehicles will you need to stabilize a freeway? Like you need one for a ring of 22 vehicles. How does that scale? And they came up with, so they did a lot of different simulations, trained a lot of different deep neural nets, and figured out that in general, with a single lane freeway, with 10% of the vehicles, you should probably be able to smooth most of the wave, which you can see, these are waves, they're bad, because that's where you lose all the energy, and this is essentially kind of a lot smoother, and hopefully a lot more energy efficient. And so for us, that was the start for trying to scale this to real vehicles. And so you can see Fengyu before he cut his hair here, and that's essentially the first time we implemented this on the hardware. So the idea is like before you tried a real car, you built a test bed, which was built by Fengyu at the time. This was at the last NSF meeting before the COVID, and reproduced the waves and then try to implement a policy transfer where you will learn the policy in software and transfer it to hardware. And once Fengyu succeeded with this, then we all traveled to Delaware to meet with Andreas to try it on some more complex systems. So this is version 1.0 of the scaled city. There's much better here now. But we tried it here on a slightly different cost function. This was done by Eugene and Kathy Jank, who is now at Waymo. So here the idea was that the self-driving vehicles are blue, and you try to adjust their speed to minimize the exit time of the last vehicle that leaves the roundabout. So it's like throughput maximization. And you can see that's the Hummer that will come last, but if you compare the time at which the Hummer or the last vehicle leaves in the baseline versus the RL case, you can see that here it's finished, but in the baseline it still has vehicles to flush out. So that was another example of transfer learning where we learned the policy in some simulator, which was also built at the scale city, to convince ourselves that, like Ilian said, we don't have any guarantees. So before we try it on real vehicles, we would like to see how well it transfers to hardware, because you learn in software, so there's a discrepancy between the software model and reality, and that gave us confidence that maybe now we can do this with real vehicles. So before we get there, I want to go back to Dan's results for the ring case. The algorithm you saw in the ring, that's actually an explicit algorithm. That's an expert algorithm. So that's something very simple, which says essentially, if you're too close, stop. If you are far, go at a target speed. And in between, do this, which is some form of linear fit of the two. Okay, so that's very, 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 very simple. So you could argue that's really not very exciting. And then, but with this, they can actually prove stability on the ring. So the ring is a simple enough system that you can prove stability using a variety of possible techniques. But from a perspective of learning, that could be an expert you learn from, and that's a cheating expert. And it's a cheating expert because it actually has a notion of the target speed. If you choose your target speed wrong, you're going to fail. On the ring, there are regions, if you do too fast, that you're going to be unstable no matter what. I mean, imagine people trying to do 200 miles an hour in a ring, there's no way it can succeed. And even automation will be very, very challenged to do it. So there is a magic speed above which you cannot stabilize in most settings. And if you know that speed, life is much easier. But in real life, you don't. Because if it's a real freeway, unless you can measure things, you don't know the output throughput, and therefore you don't know how much you can push before things break. So I'm mentioning this because that's a very good algorithm if you know this, but in general you don't. So if you don't, what you would do in deep reinforcement learning is you would train the algorithm by training the algorithm to cheat on every possible speed you could expect. So this is an example of a bunch of time-space diagrams. So again, they all do the same, like time and space. And you can see very red, lots of waves, very bad, and then super cool, no traffic. And everything in between is some form of combination of the inflow speed and the inflow throughput. And then the idea would be, why don't we train an algorithm to imitate the expert on each of these scenarios? There's one more, it's just conceptual here. Because maybe in the process, it will learn, even though in practice it will not be given the magic number, the magic speed. And we did that, and it worked really well. Not perfectly, no guarantees. But for example, if you have the cheating expert algorithm, and you cheat by telling it the magic number is 2, so 2 meters per second, you can see that algorithm does best than everybody at 2. And then you cheat again, say, okay, no, the number is 3. So then you recalibrate the expert algorithm. Now at 3, it's killing everybody else, but then in other settings, it's not. And the example here is that the blue curve is what happened with the deep reinforcement learning algorithm. When you taught it, it learned through all the possible cheating experts. And for some reason at low speeds, it's not able to learn everything. So there are some features in the flow that it probably doesn't understand. But at higher speeds, it actually is interesting that a single policy now beats all the experts, or at least is compatible or compelling with all the experts at higher speed. And so at the time, we had not done any experiment, so we were just pushing to see how could we train an algorithm so it would react to many traffic flow conditions, because we don't know ahead of time. Then we tried a few other things that also worked well in simulation, and since then we've made work in practice, which is imitation on kernel learning. So you can imagine kernel controllers. Kernel controllers are very nice smoothers. Imagine a convolution term that takes all the speeds around you, do some form of convolution, so it's like a smoothing, and then assign you the speed resulting from the smoothing. So that's what a kernel controller does. Very basic. You can prove in some cases stability with it, not always. And it worked pretty well, because you can see here, if you don't control things, first car does something weird, then the next car does something worse and worse and worse and worse and worse and worse, right? So you can see this growing instability, but with the kernel algorithm, at least it doesn't grow. It doesn't decay either, but it doesn't grow. And if you imitate from the kernel, it does decay a little bit. So that's another example of learning algorithm where we try to train it on some form of expert controller so that it will be able to react to some of the situations. And that was done by Zhe Fu, who is one of the algorithm students in the lab here. And what's to watch here is that at the end, it's not perfect, but if you look at the gradients, so sharpness of edges in here, in the no control case is much worse than in the controlled case. But again, there's limit to what you can do with a limited degree of automation, so it doesn't smooth all the waves perfectly, but it smooths them a little bit. So based on this, then we started to essentially assign cost functions to train algorithms, sometimes with warm start, sometimes with experts, and mostly with a reward function that would somehow match our objectives. So this is the actually implemented deep reinforcement learning algorithms we have now in practice. So it has a lot of additional heuristics for safety because we cannot prove that the thing is safe. But it's essentially trained on something that forces you to minimize the energy, try to minimize somehow the variance of the acceleration, because if you have a lot of variance in the acceleration, that means you're doing a lot of smoothing, and then some other integral terms to push traffic. Because if you do it just by minimizing the energy and the variance, there's an obvious solution. 0, stop everybody on the freeway. That's the best way to optimize energy. And reinforcement learning will find that solution very quickly. But that's not what you want, because you want to obviously push things. And then on top of it, you put some form of fail-safe mode, which is like completely hard box proved safe algorithm. So simple reachability will enable you to prove safety with this. And then on top of it, the car itself has an anti-collision system that comes on top of it. So we can't prove anything about this, but we have our own safety filter. And then the car itself doesn't trust us, so the car itself has another safety filter in case we fail. So from the vehicle test in 2016 and some other, by the way, you should invite Dan Work to give the talk. He has a very interesting case where they did an 8-car experiment with coordination that was really bad, like they wanted to demonstrate instability. We essentially tried to see, okay, can we do a 10-car test, and ultimately can we do a 100-car test to demonstrate that we could do this at scale with our freeway model that would work. So we first did a vehicle test in summer of 2021 in Nashville, Tennessee, because my student Dan Work, who now is a faculty at Vanderbilt, was at the time building a fantastic test bed, we'll show it to you at the end, that made this freeway the best instrumented freeway in the world. It was prior to the test bed construction, but we knew the next year when we do the big test, we would have the test bed ready. So it's very simple. Essentially, get cars to drive back and forth, 10 at a time for the beginning, to see if we could do this on one lane of freeway. So it was in the middle of COVID, it was a bit hard. We had some help of the local police to shepherd vehicles on the freeway. So it's like a typical funeral procession. You know, when you have a funeral, the police escorts you usually into the freeway so that all the cars stand together. So the police would escort us to the freeway, we would put the 10 cars in the lane, and then they would just do their thing. And with that, so it's not really exciting, it's just essentially a vehicle on the third lane, 1, 2, 3. On the freeway, this was vehicle number 7, and essentially smoothing on one lane to see if we could do it. And so this is really that setting here that you see here, essentially very single lane smoothing. And we were very excited because it was the tail end of COVID, so there was still not as much traffic as there should be on the freeway, but enough traffic to have at least 2 waves. So what you see here is the trajectory of the vehicles, and the speed is indicated by the color. So you can see this going free flow, and then one wave stops, and free flow, and then another wave, etc. And what we demonstrated with the algorithms I just showed you at the time, so no communication between the cars, just cars doing this local thing. It learned a global behavior in simulation, but then when it comes to implementation, it has no connection to anything else. It doesn't know anything about traffic, it just is doing what is learned in the simulation. We demonstrated that we can save 16% of fuel on the self-driving vehicles. So as a self-driving vehicle, you're saving a lot of energy. But then we showed that if you're the person behind, and then the next guy, and then the next guy, and then the next guy, you also save. Why? Because there's something weird. In front of you is someone who is not rushing to fill the gap, but is someone who is slowly downgrading its speed to not fill the gap right away, much smoother. And because you're behind that person, you kind of are forced to do the same. So it's not as efficient. The guy is saving 60%, you're saving 14%, and the guy behind you is 12%. But it's really great because you can see the cumulative savings over the platoon. So one vehicle creates a lot of benefits for the other vehicle. They might be road rage or they might be super furious because they want to go faster, but they have no choice anyway, and they're saving money whether they want or not. And that was Eugene Vinitsky who did that work. So that convinced us, if we did it with 10 cars, out of which 4 were running the algorithms, hopefully there's a promise that we could do it with a bigger thing. So that's what I did, was essentially explain to you what happens in these boxes. So these boxes run local controllers on the basis of local information, and unless you're giving them the magic target number, essentially they have got to base what they're doing on what they learned in simulation. Now, imagine you add to this some crappy network, your typical cell phone network, and you could feed them information, but you have no guarantee that the information will be received, and you have no guarantee that there's no more information coming, because you lose connection, etc. So the notion is now, could we create a cloud-based system that provides additional information, such as maybe sending them the magic numbers, or sending them something else that improve their efficiency? But no guarantees. It could be that suddenly you don't have any connectivity for 5 minutes, so 5 minutes they've got to be able to operate on their own because there's no more information. So now I'm going to tell you a little bit what we put in that box. So that box looks in general very crappy because unless you have fantastic information, you have to essentially buy information from private sources. So INRIX is like a standard here, and INRIX gives you a time-space diagram like this, and it's not very pretty. Essentially, you get information every minute at a granularity of maybe 500 meters. Way less pretty that you have a Google map on your phone or even the graphs I showed you before. But that's a reality. That's what you can buy. You can buy it worldwide. So the idea is you want to train a high-level planner that can use that information, even as crappy information, to provide additional information to the vehicles. And that information is interesting because Han Wang, who is a student of Mariela de la Manaque at Berkeley, demonstrated that that information, even if it's really crappy, enables you to detect this, which is a bottleneck. Essentially, there's some car obstructing things, or there's some on-ramp that is making things locally problematic, from this, which are the waves you want to smooth. So we don't really care about this. We can't change this. You can't change if some person has obstructed the street or if there's an on-ramp. You can't change that. But you can probably smooth that. So with very simple machine vision algorithms, Han was able to provide some form of automated detection that we could then use in the speed planner. And the speed planner is essentially something like the kernel controller I've shown before. Now, I want to show you something we have not implemented in the test, but we've implemented later, which is a different way of doing speed planning, which is really exciting because it's actually using neural nets, again, to compute solutions of PDEs. So if you wanted to do it the classical way, though, what you would do, and we did that too, and we implemented that, you would just use traditional optimal control formulation. So for that, you would have essentially a lead vehicle, a model of the vehicles behind, and then essentially you would optimize the cost function associated with this guy that you can control, assuming that people have to follow what they're doing. So to do that, classical control theory can be very helpful. You just model all the trajectories of the vehicles, and every time you have a vehicle you control in red, essentially you assume that you can control the speed or the acceleration depending on what model you do. So then you can essentially write this as a cascaded system, which is essentially every vehicle is following the previous one, and every once in a while there is a vehicle that you can control with this signal here. Okay? And so Arwa Alankari was a current PhD student, did that work. So she actually included the proper mathematical framework where essentially you have to define the functional space in which you're doing the optimization. So here you compute a signal in L infinity. And essentially you are going to have constraints. So you can at most accelerate that much, at most decelerate that much, and then you find the proper space in which you're looking for the solution. Then you define what's called the cost functional. So essentially some functional that takes a trajectory and a speed profile that itself is a functional of the control and has a running cost. So the running cost could be the cumulative energy you spent, plus possibly a terminal cost if you want to include some throughput. And then you can prove the existence of a minimizer to that problem, depending on the class of your running cost and your terminal cost. That means that you will be able to at least find a optimizer. Now here, because it's nonlinear, non-convex, and actually even non-smooth, which sucks, you cannot prove global optimality, but at least you can use adjoint-based optimization to find a descent direction that at least numerically makes sense. And so when we were computing speed profiles, the first idea was to run this on the cloud. And it turns out you can do that, but that's very computationally expensive. So we came up with other solutions based on kernel methods, and now we're looking at even faster solutions using partial differential equations. But to give you a sense of what it looks like in practice, this is your input data. Conceptually, it's not real data, right? So it shows you some oscillations. So what the descent algorithm provides is a desired profile in blue that would be much smoother, that would achieve the same throughput because you can't change congestion, but would be socially unacceptable because you would have to go 10 miles an hour on the freeway, so you can't do that, that's not good. So instead you clip it because that's the most society will allow you to do. If you start to drive 20 miles an hour on the freeway where people are driving 40 miles an hour, even though they're gonna stop later, you're gonna have problems with a lot of people, so you can't do that. And so essentially that's what we did using the formulation I showed before. In practice, this is what it looks like with real data. That's the crappy data I showed you from Henrix. So that's what you did as an input to the algorithm. And then the green is essentially what you get from the speed planner once you have defined your objective function, the function I showed before, and you compute your optimal signal. And that's the information you essentially pass through the crappy network. And it's going to memorize it, and it's going to have some anticipatory frame because it takes about 10 minutes to drive through that stretch of freeway. So you can use that for 10 minutes. Now, if I send it to you now, in 10 minutes, it's going to be very stale. It's like old food. So you'd rather get a version you received more recently, but at least you can probably use it for a couple of minutes until there's something else that comes through the network. And that's the reality of what you have to use when you have, you don't have V2V communication, you just have crappy networks like the cell network, and that's the way it works. And so in practice, when you implement it, that's in simulation, essentially what it does is it essentially shaves these waves to provide something a little bit more homogeneous, which is much better for energy efficiency. Okay, so that's what goes in this box. Now, I wanted to show you one last thing before showing you the results, is that in the meantime, we came up with new models for traffic which are way better than what we had before that we think we can use for the future to smooth traffic. So we did not implement this with 100 vehicles, we only implemented it with a few vehicles, but it's very exciting. And so here's the way it works. This is the basic conservation law for traffic density. So if you've not done PDEs, what it says is that the time variation of the density at x and time t is somehow related to the conservation of mass. Whatever comes in minus whenever goes out is how much this changes. So that's partial differential equations. It's hyperbolic, first order, and there's a shape of that flux function. It says that the more vehicles drive, the more flux, but at some point, if you push too many vehicles, well, traffic jams happen, and the number of vehicles going through goes down. And there's a whole 40 or 50 years war between traffic engineers who debate whether that function should be modeled as a parabola, a triangle, a trapezoidal, or anything else. Okay, models we use can do anything, it doesn't matter. But there's certainly the mathematical solutions to that problem change. And so the idea is that to solve a problem like this, which is called the Cauchy problem in numerical analysis, you need initial and boundary conditions. There's a whole proof of existence and uniqueness of the solution. And there's many solutions, but there's actually an explicit criterion called the entropy solution. And the mathematically correct solution, acknowledged as such, is one of many, many, many weak solutions, which you want to compute because historically that's what scientists have declared is the proper solution. So there's a whole mathematical characterization of it, and 50 or 60 years of numerical analysis have been devoted to finding numerical schemes that can find it amongst all the possible weak solutions. As it turns out, there's two fundamental problems called Riemann problems, which can be solved explicitly and provide such a solution. So Riemann problem is typically a shock wave Shockwave is like a lot of cars driving fast into a bunch of cars that are driving slow, and that creates a shockwave, like you drive on the freeway into a shockwave. There's an explicit solution to the Riemann problem. It's different based on the flux function you're considering, but it can be computed explicitly. And same, the reverse problem, the second Riemann problem, is an expansion wave. Lots of cars are piled up, and there's free flow in front, so cars start to move forward. And that's what an expansion waves look like. It turns out that if you look at the details of numerical schemes, every numerical solution of every possible problem is a combination of these. So you can think of this as a natural language with two words, shockwave, expansion wave. So for example, when I was a PhD student 20 years ago, I published a paper and I needed to compute an analytical solution to a problem. The problem looks like this. Okay, so you have two shock waves and then expansion waves, and it evolves like this, and that's what the time space diagram looks like. That solution, I happened to compute it by hand. That's what it looked like. Okay, so it's a pain in the ass to compute, but everywhere in every possible domain, it's a combination of Riemann solutions. And that essentially goes back to 1955 when that PDE was invented. And so the idea is that, okay, for simple cases, you can do it by hand. What if you train a neural net to do this? And so the idea is that the way numerical schemes are invented is pretty intuitive. It's mass conservation. So you cut things in small chunks, and whatever is in that chunk possibly can move here if there's room. That's all it is. So it's mass conservation. So you could actually train a neural net to be mass conservation compatible and see if you can train it first on the PDE, but then on real data. So the idea is that this equation here, which is written in weak form, in the finite volume setting, has an update equation. That's what all the numerical scheme is. But if you did not know this, could you train this to mimic this? Because then if you can do it on the PDE, you can do it in real data, and then you would have a much better model than models invented essentially in 1955. And as it turns out, the very first solution to these problems go back to 1949. And then this is the best scheme that I think was invented in the history. But even after the Godunov scheme was invented, lots of people, including Stan Osher, who is still very active at UCLA, invented a lot of better schemes to solve these equations. So for example, this is the very first historical scheme that was invented at NYU to solve that problem over 70 years ago. Godunov scheme, a bit harder to solve that same problem. Stan Osher and Eno scheme, we know, and so on and so forth. So there's like about 70 years of numerical analysis to solve these problems. And depending on the type of method you're using, the solutions can be better or worse. Like here, for a shockwave, this should be soft. So Godunov is very good. LaxRadix has a lot of diffusion. It's not very precise. And they all essentially have good features and bad features. Same with expansion waves. Same with general problems. And so the idea now, what if we instead forgot about the PDE, forgot about the numerical schemes, and then try to see if we can learn a neural net that can produce the same things on the basis of what it learns. And the beauty of this is that this is a language with two words. So all you need to do to train the neural net is to teach it on the Riemann problems. So expansion waves, explicit numerical, shock wave, explicit numerical, and then you have to have a training set that is very wide, so lots of different possible, big shock waves with here, small shock waves, big expansion waves, small expansion waves. So if you span the training set enough, then the neural net should have seen enough waves that it should be able to face every possible scenario. And it turns out that for this problem, there is an explicit solution of every possible solution, so we can also check with ground truth up to machine accuracy to check how well the neural network is doing. And the amazing thing, so we can train it on the solutions like I was showing before. And so the amazing thing here is that the neural net beats every possible numerical scheme we know of since 1949. So the way you assess convergence of these schemes is usually you have an error plot, and the smaller the cell, the more the accuracy. And what you can see is that essentially our method beats everything. And so it's very disturbing because in some ways it says people have been working for over 70 years on building mathematical models for traffic, and now with the neural net, even if you want to learn their mathematical model on their own model, you beat them. Which means there's also promise that you would beat them on real data. This is data collected by Feng Yu here, flying his own drone in China. So this is an example of the cleanest shockwave I've ever seen That's essentially a shockwave where some obstruction creates some backlog here, which you can see propagating in the waves here. Okay, so it doesn't get any cleaner because there's no on-ramp, no off-ramp. It's like the cleanest there is. And of course, that data is in complete violation of mathematical models because you can see the waves are not really parallel. And it just is not possible in the mathematical model. That would not be an entropy solution. So the point is now you want the neural net to learn something that is in violation of the mathematical model because the mathematical model just doesn't satisfy the data. And so that's what it looks like. And you can see, I mean, these triangular shapes, they're not predicted by the mathematical model. And so when I came to Berkeley, so we have several architectures here, but when I came to Berkeley 20 years ago, essentially for the next 10 years, I tried to forecast traffic with these models and I failed. And this is the first time in 20 years that I have now a model that is able to reproduce this data with essentially in violation of the mathematical models, which is what you want here, and which I've been essentially failing to do until this day with classical mathematical models. And in the same way as I explained before for the controller when we did the deep reinforcement learning and managed to beat the human-based explicit-driven controller, I think this has also very similar potential for traffic smoothing and other applications because finally we can build data-driven models that in some cases we can match the PDE, even though we cannot prove it yet, but that we can also make not match the PDE so they match the data, which is what we want for practical applications. And so essentially this is what we're putting in this box now so we can have controllers that can satisfy us. So I'm gonna just skip this because I don't have a lot of time. But when you combine all of it and make it work in practice, what it looks like at a single trajectory level is like this. You have a leader vehicle that is doing a lot of crappy things. Okay, you can see it's slowing down, going faster. It's not smooth. That's the person in front of you. And when you apply the architecture I've shown you, high-level speed planning feeds information through crappy network to local controllers. It produces a second trajectory, which looks similar for the second vehicle, but it's much smoother. You can see like here, it doesn't re-accelerate and slow down, and so on and so forth. And so that's essentially how you shave and save the energy, and that's what we managed to implement in the test. So now I'd like to show you what it looks like in the test. So this is where I really encourage all of you to go to Vanderbilt. It's amazing the test bed they've built with the I-24 motion. It's the best instrument freeway in the world. And so I'll show you how they did it. This is when they built. This is when Danwork built it. So it's not very exciting. It's like a crane. But what it is essentially they put some high-resolution video camera every 500 meters that can span the entire freeway, and with very state-of-the-art machine vision techniques, can extract high-resolution trajectories for every car on every direction, every lane, all the time. So this is the first pole they erected, and then they erected, I think, 50 or 60 poles. And the amount of data they're collecting is so enormous that I think they can only store 2 weeks of data at a time. After that, they just run out of space and out of memory. So this test bed was built in between our first test and our second test. And it opened literally the day we ran our 100-car test. And just to give you a sense of what it can do, this is different data sources, but very standard vanilla flavor machine vision technique can identify the vehicle type, truck versus pickup versus sedan, and with very simple models like the ones developed at Oak Ridge and Argonne, essentially compute the velocity-based energy consumption model for each of these vehicles, and then compute total energy saved for the entire freeway. And for that freeway, we also have class, so we know exactly how much percentage is what type of vehicles. So to try it, I'll show you a little bit of the experiment. We rented a factory. We went there, the 5 research groups, about 50 or 60 students together. And all the students built radios and instrumentation and all the hardware we needed to deploy in the vehicles. We deployed our own internet to be able to ship the algorithms directly to all the vehicles. And then we unplugged the 100 cars we had, plugged our hardware in all the cars, and then now we're able every day to ship a different algorithm to all the cars to try the algorithm on the road. So this is roughly what the parking lot was looking like. And then every day Fangi was there, and then many others helped to essentially build that test bed so we have 2 weeks of full testing of the algorithms at scale. So for example, this is the type of thing you have to do to plug in the hardware. It turns out the autopilot cable goes here, so you just open it, plug your stuff. This is Gracie Gum. She's showing us how to bypass the battery to essentially power the system and essentially put the automation. And the automation is not really sexy. I mean, this is kind of what it looks like. It's essentially a Raspberry Pi running our algorithm, but that thing is able to run the algorithm I've shown you before. So it's not compute intensive. You don't need a mega computer to do it. You can literally do it on a Raspberry Pi. And so every day we would ship a different controller, so the local box controller, and then you could check car by car. If it's green, it's there. If it's red, it's not working. So we need to figure out what's going on. And then we recruited drivers because it's only longitudinal control, right? It doesn't control laterally, so you'd still need a human to drive the vehicles. So we had to pay people $500 a week to come and meet us at 4 a.m. and drive for 6 hours and then go home. My proudest achievement is I recruited the girlfriend of my Uber driver to come and drive for this, but we had to go to the airport, to the bus terminal. We would try to do anything we could. It's very hard. We recruited 700 people, 150 passed the safety test, because you look at the police records and you're like, this person should maybe not drive that car. And at the end, we had about 150 people came to work in shifts of 100 at a time. So they would come in the morning at 4 a.m. This is John Sprinkle and Dan Work trading them every morning. And we had two teams, orange and red, orange and yellow. And essentially, we would tell them exactly what to do. They would download the routes on their phones, and then they would just drive back and forth. And then we told them, you just follow the instructions. I'm just going to skip this. So what you need to do is just press the cruise control, except just be aware, it's not running the cruise control, it's going to run our algorithm instead. So to you as a driver, you're not a professional driver, you've never really driven the taxi or anything, all you need to do is turn on the cruise controller and just, if there's anything that makes you feel uncomfortable, turn it off immediately or brake, it will turn it off, and then you can just drive the way you want. And then if you like it, just keep doing it, and then it's running our algorithm, which is complicated because then when you look at the data, you don't know always, unless you look really carefully, whether they're running the algorithm or not. So there's a little bit of data analysis to do. And then they would download the routes on their phone, scan the QR code, and just drive back and forth to collect the data. So we ran Nissan, Toyota, and XT5. The XT5 was fully reverse engineered by Fengyu, who figured out how to bypass all the possible safety things, so we could, with the blessings of GM, essentially make this car automated like the others with Nissan and Toyota. They all have different architectures. We essentially ran the parking lot like an airport. So essentially that's kind of what it looks like. So in the morning you just have people managing the parking lot, and then you just send the things on the road, and then they just run back and forth and back and forth. Once in a while, people need a break, so they come back, and then you just rotate them. So essentially, you're running your own airport for the day, while the vehicles are running the algorithms on the road. We did a press conference when we did it, and essentially, that's what the testbed measures. So this is the raw data of the testbed. This is just for visualization purposes. In practice, it's astronomical. That's kind of a sense of the data sources you get, not to control in real time. Like when we did this, this was used purely for analysis purposes. This is offline. You use that data for analysis. Now they're using it online to control the freeway with other means. But at the time when we opened it, it was just offline. So the results I'm going to show you, they're computing using that data, but we didn't control the freeway in real time. And so this is what the trajectories look like. So this is multiple lanes, so that's why they're crossing each other. So this is a car going fast, going slow, being passed by another car, and the red and the white is a self-driving vehicle. And now to give you a sense of the scale, if you've never seen a time-space diagram, these are just data. If you've seen a time-space diagram, this is the biggest time-space diagram in the world for now. And that's what a full day of data looks like. So you can see in the morning there's no traffic, in the evening there's no traffic, and during the day there's waves and waves and waves and waves, and that's where you waste all your energy. And the white trajectories here, they're not able to smooth on that day. This was a non-smoothing day. I'll show you results later for a smoothing day. But what you can see is that even if it's not visible, the savings here are already on the order of 10%. So it's actually quite amazing what it can do. By the way, this is Alex Cabardones, and this is the first time-space diagram. If you've taken any control theory, traffic theory class, this is the first time-space diagram, 1961, 10 data points over, I don't know, 20 data points. and this one is like millions. So it's like it's interesting in like 70 years or 60 years of technology how one went from this to this. And this is Alex is the most knowledgeable traffic person in the world, and so he's the one who was able to dig that very, very first diagram. But to give you a sense of the granularity, you can see these waves that are not satisfying the mathematical models, and then you can see the waves that are able to smooth the traffic. And so you can extract lane by lane data, so where things are a lot clearer, and now you can see, in fact, there is a lot of smoothing that is happening here. It's maybe a bit easier to see visually. And then you can, of course, and this is interesting, this is another result published by Fengu. So it's very hard to measure energy because it's video-based, and then you don't know the vehicle type, so it's not that easy. The data is very messy, also it's hard to figure out when it's engaged or not. But the type of plots you're looking for are essentially scatter plots. So for example, this is an example of speed acceleration plot. And this is bad because you can see people are going slow and fast. And essentially it's oscillating between the back and forth because of the acceleration. So that's where you're losing the energy. So if you compute some form of convex hull of the 90th percentile between a non-smooth case, which I showed before, and the smooth case, you can see in the smooth case, it's a better scatter plot. It's still, there's oscillatory behavior, but if you look at the numbers, there's less. Another thing to look at is the speed right in front of the vehicle on average. This is the self-driving vehicle on average over all the self-driving vehicles. And this is ahead of the self-driving vehicle, in the back of the self-driving vehicle. And you can see the speed on average in front of the self-driving vehicle is always lower than in the back, which means essentially if you're trailing the self-driving vehicle, you're on average going faster than if you're the self-driving vehicle or a vehicle in front, which means essentially you're stopping less. Another way to look at this is the energy consumption in the back versus in the front. And in the case of the self-driving vehicle, it's always negative, which means people in the back of the self-driving vehicle on average are burning less gas than in the front of the self-driving vehicle. And the numbers are pretty good. It's like 5%, 10%, some cases more. So overall, very satisfying. Last one is seeing the distribution of vehicles in the front and distribution of vehicle in the back. And what you can see is that ahead of a self-driving vehicle on average, there is a big chunk of people going slowly, but in the back, there isn't. So you've changed the distribution of speeds from something which has people stop to people going slowly gradually, and which is another way to measure the same things. And so on and so forth. So we have not established final numbers, but we do see savings that vary between 5 and 10%, which is very, very good with less than 1% vehicles. And we're still very excited to see how we can push that. One last thing I wanted to show, and then I'm really done, is now we have trained LLMs to explain to us what we're doing, because we have no idea what we're doing. It's a deep neural net. It's just the beginning, but what it sounds is like this. So essentially, this is an example of an LLM looking at what we're doing and telling us what we're doing.
The leader vehicle is currently traveling at a speed of approximately 56.4 miles per hour, which appears stable with a slight drift in relative velocity over the past few seconds. The FlowMO controller is engaged, as indicated by the value of 5 in the ACC cruise_state_int_data. Since the last planned speed in the velocity array, var, indicates a target of around 53.8 miles per hour, I am maintaining a consistent speed close to the leader's pace, which is a wise strategy given the close distance, 45 feet, to the vehicle. We're actively adjusting our speed to ensure a smooth ride without abrupt changes, aiming to stay in sync with the flow of traffic.
We don't know if we can.
56.3 miles per hour. The leader vehicle is going 55.9 miles per hour. The leader vehicle is going 55.1 miles per hour. The leader vehicle is going 4.8 miles per hour. The leader vehicle is going 4.5 miles per hour. The leader vehicle is going 4.5 miles per hour. The leader vehicle is going 3.9 miles per hour. The leader vehicle is going 3.6 miles per hour. The leader vehicle is going 3.2 miles per hour. The leader vehicle is going 3.0 miles per hour. The leader vehicle's speed is gradually decreasing over time, starting from around 40.76 miles per hour and dropping to approximately 40.75 miles per hour in the latest data.
This is the beginning of something we thought
is engaged, as indicated by the value of 5 in the ACC cruise_state_int_data.
But that we don't know. Okay, so with this, just want to say thank you again for the invitation. And I don't know if we have time for questions, but I'd be really excited to answer any questions. Thank you.
We do have time for one quick question, if there's any burning question from the audience. That, yes. Okay, we'll take both.
When you're estimating the energy savings, are you constructing counterfactuals or that say, well, had we done nothing, this would have been really true? Or were you just looking at the vehicles ahead of the control vehicle? Can you just clarify?
No, thank you so much for that. Okay. The data, so we've tried counterfactuals, but it's very hard because it was raining the day before and we only had 1 day of experiment. So the results I'm showing are not counterfactuals. We probably might do counterfactuals against statistical averages of Thursdays. The experiment was on a Friday, so or even Fridays. But it turns out we did not have good enough data to do counterfactual with this. So instead, because we can't do that yet, maybe one day again with an average Friday we could, which is also very complicated because demand is seasonal. But so because we cannot do counterfactuals, all the data we're doing is essentially done by averaging over relative position with respect to an AV to look at the distributions of speed attributes and other state attributes of classical vehicle as a function of the distance to the AV, upstream and downstream. So maybe you can say it's a geographical counterfactual, maybe, but we cannot. I wish we could do time counterfactuals because that would be the perfect thing, but we just don't have the data for it, unfortunately.
So, sorry, you mentioned about the potential for crazy people doing strange things that could disrupt the experiment, but that's already built in there because it's an experiment.
We are the crazy people.
Yeah, absolutely. What I'm curious about is what if there's another coalition of folks doing control with their own fleet of autonomous vehicles, say Ford and Citroen?
Okay. Oh my God, no. This is the problem. This is totally the problem. Because let's just pick a company like Tesla, which in some places in Silicon Valley has probably already 20% of penetration, close to some exits, like take Sand Hill Road. A lot of people have Teslas for obvious reasons there. So think about now 280 is a freeway which has a speed limit of 65, but people turn the speed autopilot on Tesla. What is it going to choose? Because actually flows goes 75. So you don't know what they're doing. They're doing something. Maybe they're doing speed limit, maybe they're doing social speed limit, which is what people are doing, maybe they're doing something different. And they're not really interested in energy savings, they're just interested in autopilot features. But when it comes to, say, our cars do this, and the Stanford cars do the opposite, because they're Stanford, then now you have a game. And if the two are not optimizing the same cost function, then it's very unclear what's going to happen. And that highlights the importance of regulation. I think that, I mean, if you think of a world in 10 or 15 years, it's not crazy to think, right now there's a speed limit. The guy who invented the speed limit in California, 55 and 65, is Bob Cannon in the aerospace department at Stanford many years ago. It's not crazy that in 10, 15, 20 years, when every car has some vehicle automation that can at least manage longitudinal speed, that the state would also say, by the way, the speed limit is that much, but also we are putting conditions on the variance and on even accelerations and decelerations in these things. Now it's technological science fiction because it doesn't scale across models, across architectures. In 10, 15, or 20 years, the state could very much do this and say, I, the state, mandate this because I know that overall it provides 10 or 20% energy. And in some ways, if you look at the FAA and the way they manage traffic, it's like flight plan management by speed. You can't dictate the speed to an aircraft, but you can dictate frequency, you can dictate route. So in some world, and this is not automated because they're still pilots, but in some ways the pilot is almost an automation tool to the air traffic controller given the respective timescales. So the notion that this could happen in the freeway is not crazy in 10 or 15 years. So right now you just get a speed limit and traffic lights. That's essentially what you have to do when you drive. But maybe self-driving vehicles or autopilots or cruise controllers in 10, 15 years, they also get variance constraints, speed and deceleration constraints that are mandated by the space. It's not completely crazy. It's not there yet, but it's not crazy.
We don't have time for any other questions, but Professor Bayen wrote some control system magazine, where they have several articles on this experiment. So you guys feel free to
You can take one on the way out. I'm not flying them back to California, so take them on the way out if you're interested in the work.
So let's thank our speaker again.